we can launch a QGIS application or also double click on the project file. In the folder where we were working, there's the project file, QGZ is the extension. I will double click on it and hopefully we will be able to start where we left. We will be able to start from the point where we left. I changed a bit the color scheme of my graphical user's interface. I hope it's more readable now. Can't get any lighter than that. It's white while it should show things, but normally this has to do with a refresh of the screen. So I will zoom out, and this is my starting point. Are we all there? All good? Very good. I would like to start where we left. We extracted from the Buongiorno Alan, ciao. We extracted from the digital elevation model our stream network. This is the only thing I am turning on right now. I'm zooming in a bit around, for example, station number 2. And this is the stream network we extracted. You remember the algorithm itself was able to subdivide the stream network in elementary stretches. Now, how good is that? How bad is that? Because our procedure doesn't see where's the water in the river. We just analyzed a digital elevation model setting a minimum contributing area to understand where the stream network starts. So the headwater component of the stream network. How good is that? How bad is that? We can compare this, which is a raster layer, with a reference polyline layer I provided you with. So I will upload a vector layer using the usual tool here, open data source. I will click it. Then I will select vector layer. Then I will browse using these 3 dots to the storing location and blue lines. Blue lines, it's our referent stream network. So I will open it and add it to the view. Pressing add. Here, down here, I don't know if you can see my cursor in the corner, lower right corner, and then close. And then, of course, I will have to look for the QGIS instance. Okay. So, it's called blue lines because this should be a stream network. We can certainly use a blue color, but above that, I would like the lines to be a bit thicker. So width instead of 0.26, maybe millimeters, maybe you don't see exactly the same value. I will just increase a bit the thickness in order to see better the blue lines. Okay. Now there's a bit of offset, as you can see, right? And this is normal. When you compare data sources that have different origins, it's normal to have a bit of a mismatch and offset in geographical coordinates. And then what else I can see from this map? If you look where the stream network ends, you can see that there's, let's say, more or less a good agreement in terms of general patterns and shape. But in the majority of cases, I'm looking, for example, at this portion here. You don't probably see the same piece of network on your screen, but it doesn't matter. I'm looking at this portion. And I see that invariably for this tributary of the main river, this river here, which is the Reno, Station 2 is Reno et Braccia. I can see that this reference stream network starts at higher elevations, right? More or less all over the places, our stream network starts downstream relative to the reference stream network. Here, 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 there, right? So we could try to improve the agreement between the stream network we extracted from the DEM and the reference one. What would you do if you would like to improve the agreement between the blue lines in that district and the stream network we extracted automatically from the DEM? What could we do? You remember there's a parameter that controls exactly that. You remember its name? The critical source area. We set it according to a general literature value, but in that area the literature value doesn't work. So what could we do? Do you have any idea? You remember we used the command R watershed. And in the window, and basically this command did everything. Sophia, is it more readable now? I did it for you.
Yeah, thank
you. You're welcome. You remember this parameter, minimum size of exterior watershed basin. We set it to 1 square kilometer, roughly, which was 1,111 cells. In order to improve the agreement between what we extract, the color lines here, and our reference, what value could we use? A higher value, a lower values, a lower value? I didn't hear you, but I saw your lips were moving. A lower one, right? Because 1 square kilometer is too big. We have to try with a smaller minimum contributing area. And this would expand the drainage network, the stream network, okay? Vice versa, if the reference blue line would have started from here, let's say, would have meant that we need a larger critical source area. So we could have used a larger one. You don't have your laptop?
Yeah, I have.
You see from there? Yes? Otherwise, there are places there. Very good. Okay, we can turn this off. And this is a layer I provided you with, but nowadays there are open resources we could use and we could access to perform exactly the same operation. So tuning that parameter, the critical source area, right? In order to have a better agreement. For example, we could open, you have this XYZ tiles among the resources in your browser. OpenStreetMap is an open access data layer we can put in the background. So if I double click on it, it's a raster. So it's a layer that covers anything that is below. It's good to drag this to the very bottom. Okay? What is this? This is a reference map. We can do exactly the same activity using this reference map. For example, I move here and I can increase the zoom. Let's zoom in with this tool in this area here. If I zoom in, this is a very detailed map, differently from the blue lines, vector layer I provided you with. Do you see? I can see torrents and streams in this whole area we weren't able to capture, right? The contrast is low. Do you see these blue lines? This is stream network that we were not able to capture. So perhaps in that area we need a much smaller critical source area in order to improve the agreement between our extracted stream network and the real one. Okay, just to provide you with an example of open access data set we could use to fine-tune the critical source area. Were you able to follow up to here? Okay. Now, let's move to the next step in the practical activity, which is extracting the contributing area of a given point where a stream gauge, for example, is located, and then characterizing the catchment, the watershed that drains into this stream gauge. Okay? Do you have Bosso et Cagli in the paper version I printed for you? Or not? What do you have? There's this section, delineate watershed for a given stream gauge. Yeah. Do you have an indication on the catchment? Any catchment is suggested there, a name and a...
It's Reno at
Casalecchio. Okay, we could do Reno at Casalecchio, or we could do Savio at San Vittore, which is the catchment we use for our practical activity in our studio. So let's work on Savio at San Vittore. It's number 5, if I recall correctly, but I could open stream gauges, attribute table. Where is it? Savio at San Carlo. I could highlight this vector and then ask zoom to feature. Okay? And hopefully this worked. Yes, we zoom to feature. You see the point here is yellow because this point was selected. If I erase all selected features, if I deselect it, it goes back to black. Okay? Sufficiently clear? I don't know why it wasn't able to upload from the internet all the tiles of the background map. Let me zoom in a bit further. No, we still have issues in uploading the map. Now, let's suppose we want to extract the basin, the catchment, draining into that stream gauges. Okay? This is our goal. First of all, we have to understand a bit the topography of the stream network, because as you can see, there's a bit of mismatch between the background layer and what we were able to retrieve from our DEM. Let me zoom in a bit further. So I'm increasing the zoom a lot so that I see better what's going on. Here, the pixels are the stream network pixels I extracted from the DEM, right? And then I have the black dot, which is the position of the stream gauge. Let me turn off the stream network for 1 second. What do we see? That there's a very good agreement between the point layer of the stream gauges and the background map. Why I'm saying this? Because normally stream gauges, ultrasonic stream gauges, if you recall from the first classes of the course, are located, very common, in on bridges, right? I see a bridge here. I see the stream gauge here. And I see that this Rio, I don't know, I cannot read the name, Rio Tamaro, is that possible? What do you read
Rio
here?
della Taverna.
Ah, okay. That little stream ends up here. This is its mouth, it's a tributary of Savio. This is the main river Savio. This is a tributary and its mouth is here, meaning that if we want to retrieve the contributing area for a stream gauge that is located downstream, it has to include also the contributing area of this tributary, correct? Why am I saying this? Because as we noted also before, there's a bit of a mismatch between the DEM from which we extracted the stream network and the background map, which instead aligns very well with the stream gauges data set, point layer. So we want to be certain that when we identify the pixel, it is a stream network pixel downstream this joint, okay, junction between the tributary and the main river. Do you remember what is used for retrieving the contributing area draining into a pixel as input data from the theoretical classes? Maybe I can retrieve it easily from here if we want to keep our slides in the background. Here and here. Okay. Watershed draining to a given outlet. So we want the overall watershed drained by a point more or less here. The only information we need as input information is a drainage direction, because then a different algorithm from what we used, also termed Salmon algorithm because it moves upstream, will use the drainage direction in order to identify all the pixels draining into a given location. Okay? Good. So let me turn on the stream again, the stream network we extracted. As you can see, there's a bit of a mismatch because this minor Taverna stream ends up here. This purple pixel still belongs to this stream. This dark red pixels are of the San Carlo River. So we need a bit of interpretation. But upstream the joint, okay? So the first useful pixel we need to use is this, dark yellow, I don't know, you tell me the color. This is after the junction, so it includes the tributary, contributing area of the tributary and the contributing area of the main stream. Why am I saying this? Because in order to run the algorithm, now we will have to select exactly that pixel. So the algorithm we use is this R water outlet. If I double click on it, nothing happens. No, okay, something happens. As you can see, there's just one input raster layer, which is the drainage direction raster. Okay? Were you able to open the correct window? So if I pull down the menu, drainage direction is what I need as an input layer. And then I would need the coordinates of the outlet point in the projection system of the whole project. But in reality, so I should go here and for example, this pixel has these coordinates. I could copy them and write them here separated by a comma. But in reality, if I click on these 3 dots in your computer, because in mine instead it will be a bit tricky. In your computer, the map should show up, and your pointer changes into a target. It did. You don't see an arrow now, you see a target. So you go to the pixel, the first pixel that is suitable with what we want to do. So be on the stream network, downstream, the join between the tributary and the main river. I go somewhere in this yellow within this yellow pixel here, and I click. Okay? If I do this operation, the 2 coordinates of the point where I click are automatically written there. I see something happening there.
We don't have the targets.
But did you click in the pixel? No? I'll do it again. So, 3 dots. I drag this down. I click somewhere inside this pixel here, and I see the pixel only for an instant. Look at the screen. I see the target, sorry. If I click, you see barely a target, and then it switched back to the dialog window. It worked? Good. Those are the 2 coordinates where you clicked. Now, we could save this raster file, but this will be for us just a temporary file, because we cannot perform any computation on the raster file. It would be a raster file, binary, a binary raster file. No data outside the basin, 1, I think, normally 1, inside the basin. So it's very good if we save it only on a temporary file, meaning that when we close the project, then that file will disappear. Okay? So I'm not changing anything here. I simply run the process. So I didn't see any red warning or error. It means that everything should have run smoothly. Let's see. I close this dialog window. Now I see a lot of yellow. If I zoom full extent, what do I see? There's basically this yellow patch upstream Savio at San Carlo. This is the area drained at Savio at San Carlo. You see this microchip icon here? It means that it's a temporary file. If you want to save it and store it permanently, you have to click there, or you have to say save this layer. Otherwise, it will stay temporary. It is still a raster. Okay, you see the icon here? It's still an icon for a raster layer. So it's better if I drag this down below the vector layer as usual. Also below the blue lines. So it is a raster layer. So if I click it and I go with the identity tool, I can click outside, and invariably I will get no data. And if I click inside, anywhere in the catchment, I will see 1. So this is a raster layer that is binary, either 1 or no data. If you are inside the catchment, 1. If you are outside, no data. As I was saying before, we need to convert this into a polygon in order to perform some basic operation for watershed characterization. There's a specific tool here under vector, if I recall it correctly, geometry tool, and where is it? Maybe it's not correct, but I have it written here. Polygonized GDAL raster conversion. So vector, no, sorry. I have probably to go raster, conversion, sorry, not vector, but raster, conversion, polygonize. Okay? Here I have Basing as the input layer, very good. Name of the field to create, it doesn't matter. It will create an attribute table with the field. But we will have a single feature, a polygon, right? So it doesn't really matter the name of the field to create. I would leave everything as is, and I also will save this as a temporary file. Because normally this command, this tool, ends up with some errors. We'll check the output after we... I think it's time for me to throw away this bottle. Okay, well, let's hope it doesn't flood the computer. I'll deal with that when we finish. Okay, too bad. My model. Okay, so let's run it. Error. So there were problems here. This is not a warning, it's an error. I don't know if you got the same error. No? So it might depend on where you clicked, it might depend on the version of the software you're using. So I am the only one with errors here. Your process ended up fine? Okay, I'll close it. Now, it says to me error, but in reality, I do see a polygon here, right? And the polygon has an attribute table associated to it with just one record. One record means one feature, so it seems to be fine. But the fact that I say error implies we do need to perform some checks. You don't have to, but you might as well. Perform the same check on the polygon you just obtained as the output. So I'm closing this. Going back to the map. Up here in vector, it should be under geometry tool, analysis tool. No. Check validity. Okay. Whenever you have an output vector layer which is associated with some error, it's always good to perform check validity. So if I perform this for the vectorized name, not for the selected feature, but for everything, it will create some temporary layer. The first one is the layer that is correct, has no issues, and it's something we can use for further analysis. Issues are saved in other temporary layers here. So let's hope that the correct one is Savio at San Carlo. Since I want to keep the valid one, I can save it to file permanently. This is output raster. We can also save output vector. So I just created a new folder for the output vector layers, and I'm going to call this vector Savio underscore San Carlo. I'm fine with the format the program suggests. The geo package is fine. The other two I can keep in temporary layer. So I'm running this. And I now have Savio at San Carlo is the correct output layer. You don't see the microchip icon. It means that it was saved permanently. And then some layers, invalid output, error output, that I do not even see on the map. Let's zoom in on this. Do you have error layers in your... you do.
Yeah, but they're blank.
So they were masked. I don't know.
It's blank. Like, it's a
Zoom to layer.
blank layer.
So there's nothing to zoom on. What happens sometimes? Sometimes you get the polygon extracted and then some isolated pixel somewhere else due to errors in the original DEM that prevent you to perform vector layer analysis. So it's always good to clean the vector layer from any error. Now that you've done everything, we should be fine. I can even erase these two because I don't need them any longer. So with the right click or two fingers, remove layers. Okay, I am keeping for the moment vectorized and basing because I'm hoping that Savio at San Carlo, the polygon has no issues, but we will see if there are issues or not. And I will save the project, which is something I forgot doing so far. Good. So the first characterization for the layer would be to compute its area, okay, in square kilometers. So let's have a check at the attribute table. Attribute table is very simple. There's nothing in it right now. And I can use this field calculator tool. Do you see it? Looks like one of those toys we used when we were kids, little kids. I don't know, they exist, these toys, still? What is the name in English? I don't know. In Italian, it's pallottoliere. In English, I have no clue. So I'm clicking this. This enables you to perform some analysis of the geometry. It comes with many functions. We will just use one function dedicated to the computation of the area. So you have a tick mark here, which is good. Create a new field. So we will add a new field to the attribute table. The field will be area in, I'll note this down to, square kilometers. So I'm going like this. Okay, in order to remember the units of this field. Then, you have already selected integer, I believe, differently from Excel, data sets in R or in GIS attribute tables are fixed. You select once and for all the nature of the field. If it has to be a string, you have to indicate string. If it has to be an integer, integer. In our case, it's a real number. So here, I should also find decimal number real, which is better. I don't know why I cannot toggle the precision, the number of decimal digits. In previous version it was possible. Now I don't know why. Can you do that? Can you decrease? We will leave 3 decimal. Not a big deal. Then if I scroll down, these are all the tools we can use. I can also see under geometry a function of the geometry $area. Okay? If I click, I get some extract from the guide, returns the area of the current feature. If instead I double click, I will see the function here. This is an area in which, if I know the syntax, I could write immediately the function I want to apply to all the features in my layer. In our case, our layer contains just one feature, which is a polygon. And I also have down here a preview of the output, right? Huge number. Why? What is this number here? 1, 2, 3, 1, 2, 3. So 580 millions. What is that? What number is that? You remember the units of our projection system? UTM? It's not degrees, it's meters. So all these functions, by default, they use the unit of the projection system. So this is the area of that catchment in square meters. We want an area in square kilometers instead. So I simply write divided by 1,000,000, 1, 2, 3, 1, 2, 3. And here is the outcome. 580 square kilometers. Okay? I can, if you want, press apply, so I can see real time what's going on, and then I can press OK. No, because pressing OK, it tried to add another field, but the field was already here. It worked for you?
Yes.
Okay. Now, this is a bug of this tool. It leaves your layer in editing mode, so you can change even the polygon, the numbers. You can tell this from the little square you see now around this pencil. It means that the layer is in editing mode. Before doing anything else, exit the editing mode, which you can do by pressing this button. Since we changed the layer, now we have to confirm that we want to save changes. So I'm saving changes, and this is the new field I just added to the layer. Okay? Very good. Going back to the map. Now, do you have questions? Were you able to follow?
Yes.
Okay. Now, another thing we can do, if you recall from our theoretical slides, another thing we can do if we have a raster layer that contains information in the background, we can characterize this polygon in terms of zonal statistics. So, statistics computed in space for all the pixels that fall into our polygon. So, for example, we could compute the mean elevation, the minimum elevation, starting from what? What raster would you use in that case? If we want to perform zonal statistics on elevation data. DEM, right? The DEM. So let's do that. Let's do that. And let's look for the tool raster. Is it raster? Let me check. Raster analysis, zonal statistics. It should be already there. But in case it's hard to find, we have all the geoprocessing tool here. So if I write zonal statistics, it's in different version. GRASS also have its tool. We will use instead GDAL tool, the tool kit that comes with basic QGIS. So if I double click on it, a dialog window pops up. Input layer will be the polygon of your catchment, right? So it's already set correctly. Actually, I know there could have been also vectorized. I had selected Savio at San Carlos, so I find it here. If you don't find the correct layer there, you pull down the menu and select Savio at San Carlo. Then, The raster layer is instead the layer that contains the information we want to compute. So here too, I can pull down this menu, select the DEM, then I have a prefix for identifying columns. Since I'm performing this operation, zonal statistic will create several fields that are not present right now, reporting various statistics that we select. The mean, the average, the minimum. So we want to remember which raster information they come from. So it's good to add, for example, DEM underscore as a prefix. Okay. Here, I have the statistics that are computed by default. Count, sum, mean. But there are many more. If I press these three dots, I can access this list and I can select the statistics I want to compute. So count, what is count? It counts the number of pixels that fall into the polygon. I really not care a lot about that. Then sum, what is that? The summation of the value for each pixel falling into the polygon. The summation divided by the number equals the mean. So count and sum are the two terms you need to compute the mean, basically. We just are interested into the mean. Then there's the median. You know what the median is? It's like the mean, another indicator of central tendency. It's the value that exceeds 50% of the values of the pixels and is exceeded by 50%. Then we have the standard deviation, so the square root of the variance of the elevation relative to the mean. So the variability of the elevation in the catchment, basically. Standard deviation is the square root, so units will be meter, like the original variable. Then there's the minimum elevation. This will likely be the elevation at the outlet. The outlet is, by definition, the minimum, the pixel with the minimum elevation. Everything drains into that. Then we have the maximum. The range is maximum minus minimum, not very interesting in my opinion. Minority is the value that is the least frequent in terms of elevation. The elevation value that is the least frequent could be the minimum or the maximum. Minimum, there would be just one value, so not very interesting. Majority instead, and we started from an integer DEM raster layer, so elevation are integers. Majority is the elevation value that is the most frequent. Do you have another way, a name for that? Is again a statistic. The most frequent value. How is it called? It's not the median is already there. It's not the mean, it's the mode. The most frequent value, it's the mode. So this is the mode, majority. The variety, I think it's majority minus minority, I don't care for that. Variance, it's the variance. So the square of the standard deviation. So if we have one of them, we don't need two. So I selected these and I can now run the tool. The computation was completed. I didn't see any error message. I can close it. Too bad it creates a new layer, temporary layer. Okay, so let's remember to save the final output before exiting. I want to show you the attribute table of the output. Now you have the area we computed previously. the mean elevation is 533 meters above the sea level. Okay, then we have the median, 506, and then we have the mode, which is not even 500. So this is the classical case of a skewed distribution. This is the frequency, these are the elevation, okay? The distribution of the pixel value falling inside our polygon looks something like this. Sorry. Looks something like this. Here you have the minimum elevation, catchment outlet, for example. And then the distribution is something like this. So that you have the mode. Then you have here, what do you think? Something like this. The median. And this is 50% of the observation. And then the mean is here. Because it is controlled by very high values of elevation that are present and are relatively frequent. Okay? If your distribution is symmetric, mode, median, mean, they are all the same. Instead, in this case, they're different because our distribution is skewed. It has a heavy right tail. This is how you say, relative to the left tail, which is skinny. It's heavy right tail. You have questions? Very good. So, let me go back to the map. Together with we could, if you are interested, please go and look how you do that. From the elevation, with the raster tool, you could compute local slopes. It generates another raster with slopes, okay? And then we could compute the average slope of the catchment. The thing instead I want to show you is the computation starting from a different raster. Together with the digital elevation model, I provided you with also the mean annual precipitation raster. Open data set from Big Bang ISPRA project. I think I showed you the landing page already. And we showed this project at the beginning of the classes when I showed you what happens in terms of mean annual precipitation in Italy. The raster we are going to use is a kilometric raster, so it's a gridded representation of mean annual precipitation, so the average from 1951 all the way to 2019, if I'm correct, a representation of the expected annual overall rainfall amount. So, I can import this raster layer, add it to the project, I mean. So raster, browse, mean annual precipitation, ISPRA Big Bang clip, meaning that we clipped it to the study area. So we will see just a tile of this huge data set that covers the whole country. I am adding it, I'm closing this window and going back to the map. It's using a grayscale representation. It's precipitation. Normally, precipitation uses a blue scale. So I can double click I can change to pseudo color, as always, single band pseudo color, then use blues color scale, and in particular, yes, it's already from white minimum value to dark blue maximum value. Press OK, and this is the precipitation. I can bring the catchment on top of that. I can collapse the legend, and for the catchment I could use a no field field style, no brush, if I want to see better the catchment and the precipitation underneath. Okay, so as we move to the watershed divide, we see higher values of the precipitation. If I activate the layer and use the identity feature, the value I read here are basically mean annual precipitation value in millimeters. So it's smallest towards the catchment outlet, it's highest towards the watershed divide. Almost double. Did you see? From 800 millimeters all the way up to 1400 millimeters. If I want to compute the mean at catchment scale, I can do exactly as I did before. So I use zonal statistic. I now have here recently used tools, double click. The input layer now it's the layer called zonal statistics. The layer, the raster layer was already active. If you don't see MAP here, map here, you can select it. We can use a prefix, MAP. Then, since now you already know how it works, I will compute just the mean. I press OK. And here, zonal statistic, this time I will save the output to a permanent file. Output vector, I will call this Savio _ San Carlo _ zonal statistic, so I remember that this is different. Geo packages is still fine. I press save. And I'm ready to run. This is the new vector layer it created, Saviet San Carlo zonal statistic. If I open the attribute table for this layer, this is the average value at catchment scale. Okay. So the area is something around 580 square kilometers, and then the mean annual precipitation is around 1040 millimeters. I can go back to the practical activity in R, and if you recall, we worked on Savio at San Carlo. The area here is 581, so very close. Keep in mind that these catchment descriptors have a different origin, okay? Particularly the mean annual precipitation one. The mean annual precipitation Savia at San Carlo was around 1042. And then what else do we have? The mean elevation, it's around 530. So even starting from a totally different data set, those catchment descriptors were retrieved using different information, we see some values that more or less agree, okay? Actually, I'm not even sure it's retrieved from totally different observation. I think the DM was the same. I'm looking at Alan because
No.
no, or different DM.
25 meters.
Okay, so different DEM. Okay, so this practical activity was for you to understand how you can easily nowadays characterize a catchment in terms of catchment descriptors that deal with morphology, the area, the mean elevation, but also minimum, maximum elevation, and climatic descriptors, mean annual precipitation, for example. But ISPRA project also have rasters that describe the mean annual potential evapotranspiration at pixel level. Okay? And this is an operation you can do for any catchment retrieved from a DEM. So even a catchment where there's no stream gauge. Our goal for the previous activities in R was to characterize the stream flow regime for an engaged catchment. You have several gauge catchments for which you have statistics in terms of mean annual flow. You can construct empirical flow duration curve. Then there's one catchment where you have zero information. You start like this. You retrieve morphological and climatic descriptors for setting up your regional prediction model. Okay, so we connected the two practical activities. So far, so good? Everything is clear? Okay. I want to show you a couple of additional things. The water is draining in that direction, but we're still safe. I want to show you another couple of things. Let me close this. No, I don't want to close QGIS, so okay. So could you tell for, let me start with the mean annual precipitation raster file. Could you tell that the pixels here are much bigger than the DEM ones? To the QGIS system, it doesn't really matter. It performs zonal statistics on raster of any resolution, right? If I turn on, for example, the stream network, which is already on, I'll drag it up here, you can very well see that the pixel of the DEM are much smaller than the pixel of the mean annual precipitation. This is a pixel for the mean annual precipitation raster layer, and these are pixels from the DEM. It doesn't really matter. It computes zonal statistics regardless of the resolution of the DEM. I think you have the specs of a given raster if you open the properties. Information, pixel size down here. It was reprojected, so it's not exact, but it's 990 more or less meters, 1,000 meters. So it's a 1 square kilometer pixel. Okay. Okay. So let's suppose you have to pass this information that took us 3 hours more or less to retrieve to a colleague of yours who does not use QGIS. And in particular, we want to save in a usable way the attribute table of the layer. We can always do that. Let me save the project. we can always do that using the export command. Save feature as. So I selected as layer Savio et San Carlo, zonal statistic, export, save feature as, and then you have a huge number of possible format to be used for exporting the file. Among them, you will see also Microsoft Office OpenXML spreadsheet. So I'm selecting this, and I am saving this where? Let's save the output in the general folder of our output vector. I created under output raster. This was a mistake. I didn't mean to do that. I'm not going to move the folder though, because if I move the folder, then the project will not find the files. So let's save the Excel 5 under the general folder here. I will save it as Savio _ San Carlo, and then I will press save. I was looking, yes. Do you see this check, add save file to the map? We don't do that because it will not have the geometrical component of the layer, so there's no need to save it in our project. You might as well remove the stick here and then press OK. Layer successfully exported and saved. Let's see if it's true. Practical activity in GIS, Savio et San Carlo. Let's see if it worked fine. I will open it up using Excel, and here you can find the values exported from the attribute table, okay, which can be useful for you to compose your report, for example, or if you want to pass this information to a colleague that is not a GIS user. Nowadays, very difficult. Okay, I can close this Excel file. Last format I want to show you. Very difficult nowadays, but let's suppose you do have a colleague who does not have any GIS capability. He can still see the catchment you extracted using a web-based Google resource, which is Google Earth. So, in order to create a layer that is visible on Google Earth, we will export this data set to KML format. So we'll do exactly the same operation. Save feature as, instead of Excel, we go here, K-hole markup language. This is a format that can be read by Google Earth. And let's save this file again under practical activity in GIS. Savio. Okay, I save it. There's no overwriting problem because this comes with a different extension, KML. So it will not overwrite the Excel file. I press OK. It's good to save the existing feature polygon 1. layer exported successfully, so we should be fine. Here, I now have also a KML layer. Probably I didn't untick the add the exported layer to the map, and in fact it's here. Not that I need that. So I could remove this layer together with all the temporary file, if we want to clean our project, all the temporary file that we do not need. You can select more than one file with control.
In zonal statistics, it's the one that you wanted to save. That you said we need to save it.
No, not necessarily. Zonal statistic was the first output when we analyzed the DEM. We don't need to save that. We don't need to save this, and then pressing Control, I can select also this layer, and then remove layers. So I have cleaned my project. I save it, and I want to show you what we see if we upload now. Are there problems? No. All good?
Yes.
Need any clarification from my side? I want to show you how you can see this output in Google Earth. Do you have the client version which works better or not? You don't have it? So I used to have it, now I don't. Let's find Google Earth. This is it. We can launch it, and we can explore Google Earth. Now, it stayed in the mountains, but we can zoom back. And perhaps you have a different view. I can set the map to north and remove the tilt. So it should look something like this, also in your case, right? Now, File, Import File, Load from this device. I can go to the desktop. Practical activity on GIS. Savio at San Carlo is the only file in KML. I can open it. Livello dati, sperimentale, elementi mappa. I don't know. I am selecting elementi mappa. So it's creating a polygon. See, that you can see in Google Earth. Now we can visualize it using the digital elevation model that Google Earth uses for warping satellite images. So, for example, we can look at our catchment from the outlet. We can tilt and we can zoom in. And if you zoom in, you will see that even though we use a different digital elevation model, our identification of the drainage divide is rather accurate. Do you see it? I'm zooming in. I'm moving it so that you see the three-dimensional effect, because if I stop, it's not that visible any longer. This is the drainage divide we obtain using a totally different digital elevation model. Okay? Do you have questions? So far so good? No questions? Okay. Now, last thing I want to show you concerning the practical activity on GIS is an example of a report, right? Which will have the usual structure. So, description of the data set that I provided you with, theoretical elements and outcomes. If you recall the practical activity, the assignment is to perform everything starting from a different catchment. And then you can check if the outcome you get is similar to the values I provided you with in the table of the first practical activity, as we did today. Okay? So Alice performed her computation looking, I think, if I recall it correctly, Reno et Trachia, the little mini tiny catchment we have. It's the report, which can be very, very, very brief, as I always say, starts by listing the material. Maybe this part is less important. More important is to have some theoretical elements for you when I will ask a theoretical question. How does the 8-direction 4-point model works? The D8 method, for example. Now she retrieved some images from the slides and described theoretically all the steps: critical source area, contributing area, and then she started to work on Reno et Trachia, retrieving the catchment for that string gauge. Where is it? These are all the steps associated with the elementary basin. She captured images from the GIS with the screenshot and pasted in the report, which is fine. QGIS also give you the opportunity to generate print layout with, for example, the scale bar. We did not have time to show you application on that. Concerning the report, I'm perfectly fine if you take screenshot from the application and use them as images in your report. Here she's showing the fact that perhaps we need a smaller critical source area. This is the watershed delineated for Reno et Trachia. And these are some zonal statistics computed for that catchment. Okay?
Okay.
Is the more or less the template of the report clear? You know what you do? Very good. So I can close this. I can save the project. In order to perform this application for a different catchment, you don't have to start from scratch because you already analyzed the DEM with the D8 algorithm. So the component r.watershed, you don't have to rerun. You simply do what we did today. We use r water outlet and then the characterization. You have questions? No questions? Okay, since we still have some time, did I save? Let's save this. And let's close QGIS. And stop Teams connection. Okay. Since we have some time, I would like to start addressing the last theoretical topic we will have in this module. So let me go here, my files. Where is it? Here. And and reservoir sizing. Download. I want to point out a couple of things. I want to point out 3 things. Did you register to the field trip? Can you come?
Yes.
All the people that are almost sure that will take part to the field trip, they have to register, because otherwise it would be impossible to get you on the bus.
Quick question, if I'm on the, if I registered Serenity online.
Okay, yes. The important thing is that you are somewhere, either there or here, but the important thing is that you fill this form if you want to attend. Then, I wanted to show you, maybe you got also a message, an update from Virtuale, that I uploaded these slides, and I also uploaded the last practical activity. This is a totally new subject, a new component of the module, because this year the module, let's say, focused more on hydropower. Okay, it was different since last year. So new theoretical slides and new practical activity. Practical activity will be in R and will be quick. Perhaps we'll be able to deal with it on Wednesday. In that case, Wednesday will be our last theoretical class. We can meet after Easter break in order to just have a chat on the syllable, the course, the component, and rehearse our exams work. Okay? But first we have to address this part. I'm pointing out that it's a new component because I hope slides and practical activity will be sufficiently clear. If they're not, please do ask questions and please comment them, maybe also in the formal surveys we will run at the end of the class. But if you tell me, it's even better. Okay? Let me know if everything is clear. Now, since we skipped the break, I'm not going to end this class sharp at 1 o'clock, but since we do have some time, we might as well address theoretically the last component. Okay, so we're still in the hydrological component of this class. The technological one will start after Easter break with my colleague Cristiana Bragalli. We are still in an area of water balance, understanding the availability of water resources in order to know how much water resources we can safely use. No? We saw how we can summarize the stream flow regime through flow duration curves, and this is great if we deal with a micro hydropower plant or mini hydropower plant, which are normally run off the river plant, meaning that they use the water that is available. They have no storing capabilities. They use the water when it's available and for how much it's available to produce hydropower potential. But large plants, particularly in mountainous area, may use reservoirs. Reservoir can store for a given amount of time water in order, for example, to have a more stable and constant throughout time turbine flow, so that we can send to the turbine a constant discharge. Why? Because in that case, we maximize the plant efficiency, because we can have the turbines working at the turbine flow they are designed for. The flow, the discharge they can use, maximizing mechanical and electrical efficiency. These are already technological components, and you will address them next module. But still, we're now interested in understanding if we can size the reservoir, so assign a capacity with an objective clear in mind. So what we will be presented in this last theoretical component is a rule of thumb, first sizing method, okay, simplified sizing method for identify reservoir capacity for a power plant that can use a reservoir. It's not a run-of-the-river plant anymore, it's a reservoir power plant. The method we will be using will be a simple one, and again a graphical one. You will see. We will make use of the mass curve. I don't know if you know what mass curve is, but basically it's the cumulative volume of inflow water into the reservoir. This method for sizing reservoir capacity is also called ripple method. I don't know if you heard of this in other contexts. We will work with a very clear objective, understanding, given the amount of water resources flowing into the reservoir, understanding what is the needed capacity in order to have a turbine flow that is kept constant throughout the year. Okay? This is the reservoir. We will have some inflow from upstream. We will have mandatorily to release environmental flow, so we have to take that into consideration. We cannot use all the water resources coming from upstream. We will have to release downstream the environmental flow defined by regional regulation. And then, depending on what is left, sizing the reservoir capacity in order to have a turbine flow that we can keep constant throughout the year. I already pointed out that normally when you design a hydropower plant, you also select some turbines. Turbines have functioning specs, and they maximize their efficiency relative to a very well-identified turbine flow, okay? So in order to have the turbines working at their full capacity in terms of efficiency, we want to understand what is the flow, the likely flow we will be able to send to the turbine array with a constant discharge throughout the year. You know very well from the streamflow regime component of my module that streamflow vary in a huge way. Natural streamflow are extremely variables, and we need to take this into account. What you have here is a representation of streamflow regime in a given river cross-section, okay, represented as three lines, a black line, a blue, and a red one. What do they represent? The black line is the chronological evolution of stream flow in a typical, from a climatic viewpoint, year. If there's a reservoir that we have to size, we cannot look at flow duration curve any longer, because if you remember, flow duration curve destroy the chronological order of stream flows, whereas here we are interested in the evolution in time of stream flow. We have to keep the chronological order of stream flow well into account. So the black line here, what is that? This is a 30-day, so basically a monthly, a window, a time window that moves of 30 days. It's the average in a 30-day window of the median stream flow regime for a given year. Behind this representation, imagine to have the real stream flow regime observed for 10, 15 years, okay? You take the median of the stream flow regime to get an indicator for the typical year, and then this would be a curve with a lot of peaks. We will see that in the practical application. In order to stabilize a bit the score, to smooth it, you take an average of 1 month, a moving window on 1 month, and you take the average of the median stream flow. This is what happened in a typical year for a climatic viewpoint. Okay? But then, if you look at a very wet year, things might be very different. The blue line, exactly same process, but not the median regime. Now is the 1 in 10 year wet year. So it's associated with a non-exceedance probability of 0.9. Very similar to what we did with annual flow duration curve, if you recall them. So very, very different. The only difference here is that we do it with stream flows in chronological order. And then, again, you could look at difficult years in terms of climatic conditions, dry years, and the situation, again, could be like you see here. So the wet season on a dry year, you see a discharge for the very same catchment of, 3 cubic meters per second, and in a wet year, above 30. Again, we know this very well. Hugely different stream flow regimes depending on climatic conditions, right? If you are to size a reservoir and your objective is, in the long run, for years to come, to be able to send to the turbine a constant discharge, and you look at the reservoir capacity on an yearly basis, my question for you is this. In order to size the reservoir, would you look at the typical regime? Would you look at a wet year? Or would you look at a dry year of assigned probability? Here we use a return period of 10 years. We could do a similar diagram for a 5-year return period. I'm not saying which return year to consider. I'm saying which curve to consider between the red, the black, and the blue. If you are to size a reservoir that then has to provide a turbine array more or less with the same turbine flow, no matter what, no matter the climatic condition, because you buy your turbines with a, let's say, design turbine flow, which you would like to keep constant for 50 years in which your hydropower plant operates. Would you look at the red curve? Would you look at the black curve? Would you look at the blue curve? The blue. Why blue? And you?
I would look at the minimum.
You would look at the red.
Yes.
So convince yourself. Why the red?
Because I need to look at the minimum water that I can give to the turbine, because I can always just have more water than what I need. But if I have less, how can I use the turbine?
Exactly. Because you could look at the blue, meaning in the blue, I know that I will produce a lot of hydropower electricity, but the constraint of the problem is that you have to send every year the same volume, the same constant discharge to the turbine array. Because when you pick from the catalog a turbine, it comes with a design turbine flow. And I want to send that flow on a wet year, on a typical year, and on a red year, or on a dry year. So if I focus on this is something I observe on average every 10 years. I will then be able to have this power plant working at its design capacity on average 1 year, because all the other years will have on average lower stream flows. So the correct way to address the problem is to look at a dry year, not even a typical one, because every other year, if you look at a typical one, every other year you will not have enough water to run your turbines, right? Not even a typical one. You will look at a certain dry year. Okay, I wanted this to be clear. So, what do we need to perform our sizing? We need data of discharge. Monthly, they can be monthly, it's fine enough. Even better if we do have daily data to use for the sizing. Or it could be an ungauged site. And in that case, we will use regionalization procedure to predict the diagram we just saw, using observation where they are available. Okay? With very similar approach to the approach we saw from for flow duration curves. Then, of course, another information I need to have, it's the E-flow for natural streams. But this is an information that comes from the water manager, okay, the river basin authority. They are in charge of defining the E-flows. The hypothesis, well, we have to select how we define hydrological here. Normally, it's common practice in this hemisphere to look at the year starting October 1st and ending August 31st. That's the hydrological year in northern hemisphere as convention definition. But we will look at calendar year, define it from January 1st all the way down to December 31st. Then we will assume that there's no climate variability, but this is an ingredient to take into consideration and assess if in the long term the water availability is projected to be the same. Otherwise, I will build a power plant today that in 20 years from now I won't be able to use, right? So if there are hydrological projection, I might as well have a look at them. We will, for the sake of simplicity, we will look at we will work under a stationarity hypothesis, and then we will select a reliability level. This is exactly what I wanted to point out before. We want our power plant and our reservoir to be reliable, and the reliability level you express in this way. It's basically the non-exceedance probability, the exceedance probability of the dry year you consider. You want to look at climatic conditions that are exceeded very often. Okay, if they are exceeded very often, it means that you will have more water availability than the water availability you designed it for, right? So the jargon in reservoir sizing uses reliability, but it's actually the same thing as return period, okay? Here you see different power plant. So if you have a larger reservoir, normally you look at a 90% or a 95% reliability. What does it mean? It means that your reference dry year will be a dry year with a return period of 10 years or 20 years. The higher the return period, the higher the reliability. Okay? If you are working on a small or medium reservoir, you do refer to a lower reliability, 80–90%, which means a return period of 5 years or 10 years. And then super large reservoir would look at multi-year time interval, not just a single one. And when they are designed in practice, they also look at sequences of critical dry years. So one dry year after another. They work in the worst case scenario because what you're sizing, it's a huge reservoir. And huge reservoirs are associated with very large costs, for example, in constructing the dam. You do not want to oversize a large reservoir. It would be very, very dramatically expensive. Okay, this is our working environment. It just sets the scene. We will start from here on Wednesday. Okay, good. I'll see you on Wednesday.
But, excuse me, Professor, how do we know this?